Hi, everyone. So I'm Stephanie of the Stephanie and Pat Pair. We do this really cool content series called Drive Stats. And Drive Stats is at Backblaze. We run data centers. And we've been tracking the failure rates of those hard drives for about 13 years now, which is pretty cool. And if you were a Backblaze customer, you would be storing your files in our cloud. And it is all these hard drives. So we love talking about it. Did I not turn it on?
Turn it on.
There we go. All right. So, meet the Drive Stats team. I'm Stephanie. My title, as I was just saying, is not very impressive. I'm a writer. But what I do at Backblaze is a lot of technical storytelling. But Pat is our chief technical evangelist who carries on with the other half of my story. So, as I was describing just a moment ago, I do a lot of your big picture stuff, data analysis, talking about the overlap between data centers and temperature and power, all that good stuff. And Pat digs in on technical how-tos. Let him introduce himself.
Yeah, so I'm Pat Patterson. I have the marvelous title of Chief Technical Evangelist. Stephanie's work is more impressive than her title, and I'm kind of the other way around. So, but I write code, write articles. Basically, my job is to explain how things work to hands-on technical professionals. So I don't see myself as a marketing person, I see myself as more of an educator. I was a developer for 10 years before I did this, and I've been doing this for 21 years now, which is rather alarming, really.
I mean, impressive.
But we team up on Drive Stats. I do most of the data engineering side, so getting it to the point where we have those tables that you'll see in a few minutes. And then Stephanie focuses on interpreting that data, comparing it to the past results, pulling out the trends, and so on. Yep. So it's a lot of fun. Yep. All right, let's get started.
Jump in. So just to give you an idea of what we're doing today, so we're going to talk about hard drives. And contextually, everybody's been saying, oh, the hard drive's going to go the way of the dodo. We've got SSDs now. But the truth is that hard drives still make up the majority of data center storage worldwide, and in an era right now of massive data growth, this is a huge deal, right? So we're going to talk about that. We're going to talk about some stats. We've made some really cool upgrades to the data engineering side, which is something Pat's going to demo for you live. We love a live demo. And then we're going to talk about how long hard drives last, and a little bit more about like SSDs and HDDs and how they exist in a data center. So let's talk a little bit about the state of data right now in our life. This is a map of power in data centers in the United States. Okay, this is data that comes from 2024. And this shows you, when you're buying data center space, you do it by power. So when you look at something like this, where you have large concentrations of power, you know there's a ton of data centers there. This is a very power-heavy operation we're doing at all times. But of course, the United States isn't the full story, although traditionally about, what is it, 50% of the world's hyperscalers, so AWS, Google, everybody like that, have been here. This is what the international market looks like. This is 2023 data, so that's really important given the growth of data centers recently. But it gives you kind of an idea of where other data center regions are. You can see some of these hotspots. So there's a lot of compliance related reasons that there are data centers in Europe specifically. If you've ever heard of GDPR, it tells you about data storage privacy and all those good things. So you've got stuff like that happening, and then similar story in APAC, right? So there's interesting developments happening in this front too. If you pay attention to anything that's happening in the Middle East or even in Latin America, there's going to be more development around this soon. It has a lot to do with our ability to get cheap power. By the numbers, this is how much data we're looking at. In 2024, the data created, copied, and consumed was 149 zettabytes. Putting that in understandable numbers, that is 1,000 exabytes or 1 billion terabytes. Since we talk about hard drives in size of terabyte at the moment, right, because they're getting larger, we're going to go ahead and talk about it in terabytes. And then just digging a little deeper there, as I mentioned before, about 80% of data storage in data centers is still on hard drives. So that's your spinning disks, right? Old, reliable. And there's a lot of good reason for that. This is where Drive Stats comes in. What is Drive Stats? Since 2013, we've collected and published these stats. It's in an open source database that lives on our website. You can go to it right there. Every quarter we update. We collect smart stats from our drives every single day. So this is a huge data set. We have recently started maintaining an Apache Iceberg table as well. Iceberg table. Do we still do that?
Yeah.
Okay, great. Pat's going to talk a little bit about why that matters. But if you're wanting to do your own projects, this is where you would go download it. And if you do, let us know. We love hearing about everybody's projects. We were recently talking with some folks from England who are doing a whole paper, and they had a bunch of questions about the data center or data stats, and we talked to them for well over a week. So it's going to be cool. Annualized failure rate. What is this? We take total number of drive failures, divide that by your drive days, so that is every single day that has existed in this quarter, and then multiply that by 365 and by 100. That last 100 there is your percentage marker, but the 365 is important because what it does is it says this failure, if a failure were to happen per day, this is what it would look like, right? So instead of being just within this 3-month period, it normalizes your number per the year. At a high level, we've got 6 data centers in 4 regions. So that is about 5,000 storage pods. Storage pods are what we call our servers. Within each stored pod, you've got 20 drives per pod.
60.
Oh, I'm sorry, 60. Looking at my own slides here, guys, sorry. So 60 drives per pod. And then you have, so that means about 320,000 hard drives at this very moment. Our pods, like I said, collect stats. They write that XML to a B2 bucket. That's our cloud storage, of course. Java app converts that XML to a CSV. We ingest that into Snowflake, which is a data warehouse. And presto bango, you have analytics. Generating drive stats. We'll let Pat take over here.
All right. Awesome. So, everything's based on a tool which who works with hard drives and is into this stuff? Okay, so you've undoubtedly heard of SmartMon tools. So this is how we get those smart stats from the drive. So SMART, it's an acronym, isn't it?
Yeah.
It actually stands for something, and
Yes.
nobody ever remembers
No.
what it is.
Yeah. I mean, I've written an article about it and I've forgotten.
Yeah. So basically, like drives have about 150 metrics that they can tell you, and you can say to a hard drive, "Give me the smart stats," and they are things like number of uncorrectable errors, power on hours, maximum temperature that the drive has experienced, all these statistics, these metrics for each drive are collected by this SmartMon tools. And then we have a C++ app that puts together some other attributes. So things like the date, the drive serial number, the drive model, and so on, and drops it into an XML file. And by the way, one of our values at Backblaze is transparency, and we've always talked about this. And so we talk about this in quite a lot of detail in a couple of blog posts there, but just Google Backblaze Drive Stats deep dive or whatever, and you'll find it. So one of our engineers created this marvelous diagram with ellipses and arrows, which I'm going to step through. No, I'm not. But it looks cool. It's like, hey, I did some work. But so we gather these statistics, as Stephanie mentioned, that they go from XML to CSV, and we push them into Snowflake. So a data warehouse is like a big database, but there's some key differences. So if you think about a relational database, like Oracle or MySQL or so on, they're very much optimized for row-by-row data. So you're, say, adding transactions to a table or adding customers to a table, and quite often you want to go to a particular row based on an index and pull that row back. So you might want to pull back a customer based on their customer ID, and you want their name and address and everything to do with that customer. That's great for operational databases, things like logging transactions, things like appending rows of data. When we actually come to analyze that data, quite often we're doing things like looking at all the values in a column. So I want the sum of this column. I want the minimum and maximum values in that column. And that pattern of access is very, very different. So we have this idea of data warehouses that are oriented around columnar access. And we'll see in a minute that this is very, very efficient for this kind of data. You can do a lot of compression and so on when you're organizing the data by columns. So there are many, many choices. We happen to choose Snowflake, a very popular cloud data warehouse. And this is what some of the raw data looks like in the Snowflake web UI. So the pod, so this is the identifier for the server, the date, which cluster it's in. So this is in our original cluster 0. Pods have a serial number that only these ones are set and so on. But you've got things like there, maximum drive temperature, CPU usage for the pod, and so on. So these are some of the raw data. And when we build the Drive Stats dataset, we combine all of this together. This is what Snowflake's doing for us when we say we want Drive Stats. So Drive Stats is a table where each row is drive serial number, drive model, date, all those smart stats, and crucially, whether the drive failed that day. Almost all of the values in that column are 0. Some of them are 1s. And in order to compile those, what used to happen, so has anybody been to a previous version of this talk in previous Def Cons? Okay, so previously, our colleague Andy Klein, who's now retired and gone off to play golf, did Drive Stats, and it had evolved as a very manual process where Andy would go and cross-check JIRA tickets for that said this drive was taken out of the pool. Did it actually fail, or was some operational reason we swapped it out, whatever, in order to make sure the data was all clean. But now we kind of have like this, oh, there it is, JIRA ticket. So we're aggregating data from JIRA and other operational systems into this view of the of drive stats. I don't know, this is great. Source drive stats dynamics, so this source drive info. So this all rolls up into the table we'll look at in a minute. So traditionally, historically, we have published that data as zipped CSV files. So if you go to that backblaze.com/drivestats, there's like a zip file for every quarter going back for 12 years. Yeah, 2013. First couple of years, they're annual, and then the zip files got too big. And that's cool. CSV, very accessible format. You can pump it into any database system. You can open it with Excel. It's kind of human readable, but it's really not efficient for running analytics. Okay, to kind of sum that failure column, we would need to read every character of the file because it's laid out row by row. So there's a file format called Parquet that is a columnar file format, and rather than being ASCII, it is binary. And you can get really good compression with columnar data, because if you think about that failure column, where it's almost all zeros, you don't have 0, 0, 0, 0 1,000 times in the encoding. You have run length encoding, so it says there are 1,000 zeros here, and suddenly you're only taking up about 4 bytes instead of 1,000 bytes. So it turns out that this is very efficient, and it's become kind of the lingua franca for cloud analytics. So Parquet is the file format, and then Iceberg is a table format. So Parquet says, okay, this is how you organize the data file by file. Iceberg says this is how you take a collection of those files and treat them like a database table. And then we use a tool called Trino, which is a SQL query engine, to run arbitrary SQL queries against these files which are stored in Backblaze B2 in the cloud. The snake is eating its own tail. We're storing our metrics in the system that we're measuring. Inception.
I love it.
So yeah, and this is my favorite bit, and also the most nerve-wracking, because I'm going to show you live how this stuff works. So, unlike yesterday, I'm not going to show you my email folder and calendar. I have this app, this SQL engine, Trino. It's running in Docker. It keeps its metadata in MariaDB, so a fork of MySQL, and it uses this Apache Hive metastore service. But basically, Trino is the main thing here. So what we can do is we can get a CLI, and how is that looking at the back? Shall I make it a bit bigger? Is that better? Okay, cool. So we're in here. So if we say describe drive stats, this is it's one table, and you can see here date, serial number, model. Oh, capacity, drive capacity, really important. Whether it failed, and then all of these smart stats, smart attributes. And then way down the bottom, we also added some more metadata here. So which vault? So in the way that our system works, you have 60 drives in a pod, 20 drives form a vault. And so when you upload files, they go to a particular vault, sharded into 15 data shards and 5 parity shards. So that's what a vault is. And so we have like what vault the drive is in, what pod it's in, what data center. So we can do some really cool analytics now for do drives behave differently on the East Coast and West Coast? Do our particular positions in that pod more likely to fail? Maybe they're closer to the power supply unit. Maybe it's a bit warmer on that side of the pod. All of this information is there for our analysis. So 197, it says rows there, but each row is a column. 197 columns in the data. So very, very cool. So like the first thing we want to look at is, okay, how much data have we got? And we talk about drive days. A drive day is a drive running for 1 day. And so 621 million drive days of data. So there's 621 million rows in the database. And then, okay, what time period are we talking about? So I'm going to get the min and the max date and also do a nice little formatted calculation here. So it takes a little bit longer to get this because it's actually got to go and scan through that date column. But considering it's got 621 million rows, it's pretty efficient. And I've got this character view, but I can also, I wasn't fast enough. There's a GUI that you can like see this in as well. But so we started collecting data in April 2013. And so our cutoff for the last quarter was 30th of June. Now this is just because I created a view on the data set with the data up to the end of the quarter, because that's how we do our analysis. In reality, if I went back to the actual source thing in Snowflake, that would show yesterday. So that's 12 years and 2 months of data we've got. And we can look at other cool things. So how many drives were we operating back in 2013 compared to today? So, 21,000 in 2013, 321,000 today. Pretty impressive that it got that in 1 second. So Trino has been and navigated multiple Parquet files to collate those counts. So that's a 15-fold increase, but drives have gotten bigger. So if we look at how many petabytes of storage we were managing then and now, 54 petabytes back in 2013, and what's that? It's close to 100 times as much now. And so, looking, I don't know if there's any data SQL nerds here. It's so easy, like select date, sum of capacity bytes, so like just the capacity of each of those drives over 10 to the 15 on those particular dates. So again, it's summing that column, it's pulling back that data incredibly quickly. It took less than a second to do those two sums. And so I know what you're all thinking. You're thinking, wow, Pat, what's the compound annual growth rate from when you started until now? What's the average growth per year? So that's 45%. So think about that. 45% per year for 12 years. That's the demand for storage, and why we've got 100 times as much storage as we had. So there is all kinds of fun here. Like we have queries here that pull out bits of the model number to give you a nice human readable manufacture and all kinds of that. I'm not going to go into too much more detail, but it's kind of fun to do some ad hoc querying on this size of a database, on this data set. And the really cool thing is you can do this yourself. So if your imagination has been sparked and you're thinking, what could I find in that data set, in those 621 million rows? I wrote a blog post, Iceberg on Backblaze B2. So this has read-only credentials to access those files in Backblaze B2. And I give instructions for Snowflake, Trino, and DuckDB, but pretty much any analytical tool that's able to read Iceberg, you should be able to make it work, just adapting the same instructions. If you run into any issues, email me, pat@backblaze.com, and I would be very happy to help you get it working on another platform. So, it's back to Steph for the analysis.
Jumping in. There's also a video, so if you're a person who doesn't love reading articles, we've got you covered. Pat is a great presenter, as you can see, very easy. So once we've gotten through all that, data restructuring, our biggest concern was really just making sure that it matched up with what we were doing before, right? Especially when you've got a lot of manual data cleanup, like hats off to Andy. Before we moved to Jira, by the way, we were on a different data center work ticket. So he was actually not even able to query those data centers. This man was looking at thousands and thousands of data center work tickets to make sure that a failure was not an actual failure and not a loose cable, right? So we were actually super impressed once we generated your first table here to see how consistent the numbers are. So when you're thinking about the quality of the data set, no, Andy did a great job, honestly. So let's talk data. The quarterly data, we've got Q1 and Q2 to look at here. And the reason is really simple. I think I'm not going to go through this table line by line. But I know, right? Everybody loves a line by line. But you'll see quarter one, we had 1.42% as our quarterly failure rate. And then if you pop over to Q2, this report just dropped on the 5th. It's 1.36%, right? So you can really see a pretty big jump quarter to quarter. And the reason for that is that some drives just act really different quarter to quarter. We're not really sure why. But you can see here, you've got the Seagate model here with a 9.47% failure rate, right? But if you pop over to the next quarter, that same drive only has a 4.74% failure rate. And you'll see that much variation because, especially when you're thinking about the way drives enter and exit the drive pool, you've got fewer models, and that really telescopes a single failure into looking like a higher percentage. So it's always worth looking at different columns of these quarterly analyses to see what happens. And of course, I go in depth on everything in those reports, and you can check them out. But the long and the short of it is, over time, what we've realized is that when you're tracking drive failures, there are some things that create broad brush patterns, right? Gets older, end of its lifespan, it's going to have more failures. But even when you're looking within like a manufacturer to manufacturer comparison, you don't have a lot of, Western Digital is the best or the worst. Like, it's really model dependent. So when you're looking at buying storage for yourself, this can be really helpful, both when you're looking within your 12 terabyte or drive cohort size, manufacturer, whatever. But remember always that in a data center, we use drives way differently than a consumer does, right? So you might get a totally different life cycle out of it because we are running them as hard as they possibly can every day until they die. So lifetime data. As you can see, quarterly data changes pretty significantly. So the lifetime data always gives us a really cool view, partially because we have a little bit different exclusions. You can see that here. We have more drives before we can throw them up in this table. But you also see some really interesting things. So this is a view of all the drives that are existent in our current drive pool that right now have been going, right? So when you look at this drive count, that says this model has this many drives right now, and this is the average age in months. So you can tell from that drive is a little over 5 years old. And you'll see some really interesting things with this because I just said, as a drive gets to the end of its lifespan, it's more likely to fail. But these two at the top here, you've got 82.7 months, so over 7 years. Same thing here, 80.2. Those are incredibly low failure rates, lower than the average, right? So what does that mean? And that brings us to some fun analyses we did today, talking about the bathtub curve. And Pat will give you a little more when we dive in by cohort. And just, make it pretty. Thank you, creative team. This is lovely. This is your snapshot. But it gives you an idea of what drives we have by percentage by manufacturer. And then when you get in, before we go over to Pat, I just wanted to give you an idea of how different this can be when you're talking about per manufacturer in the drive, right? So you've got this guy is your blue line here, right? Q3 2024, we're seeing high failure rates, but why, Same thing, Seagate, great over time, really low over here, Toshiba, and then Western Digital. And then if you look on the next slide, you see a really similar story to what we saw in the quarterly data, right? So these can jump pretty significantly, and it has a lot to do with drive count. And also our buying behavior. When you're buying for an enterprise drive company, it's very different, right? You're going to be buying tens of thousands of drives at a time, maybe hundreds of thousands of drives at a time. So always good to look at what the population of the drive is before you over-index on those percentages. We bop it over to Pat, talk about how long drives that last, or hard drives last, excuse me.
All right, thank you. So this is like a classic diagram for reliability engineers, the bathtub curve. And there's this idea that, when we're working with many, many different kinds of components, equipment, anything kind of manufactured, you see this kind of pattern where if you look at the red dotted line, you have manufacturing defects that cause equipment to fail rapidly after it's been deployed. So you think of like when you get a new car and it turns out to be a lemon and you end up taking it back in the first week because it's making a clunking noise. So these are faults that are kind of inherently there and show themselves quickly, these infant mortality failures. And then as time goes on, you have just a random failure rate. Just over time, anything mechanical can break. There are many reasons. Maybe it's been mistreated. Maybe it's like had a little more wear than its peers. And you have this green line of just a constant background failure rate. But then as equipment ages, we see the failure rate rise because components are starting to wear out. And this is particularly true for hard drives because remember, they are spinning disks. They are moving all the time. And well, our hard drives,
Yes.
we do not spin our hard drives down. They're spinning all the time. The heads might not be scanning across them all the time, but they're certainly spinning. So we do have this pattern of increased failure rate when equipment's introduced, kind of things settle down for a while, never to zero, but a low failure rate. And then as you get into this wear out period, it rises. That gives us the blue bathtub curve. And we've actually taken a look at generating these curves from that data, from that data set. We first did it in 2013, and when we did it the first time, we hadn't been collecting data for 4 years. So what we had to do was look at the power on hours, at the beginning of the data set, to see how old each drive was. And then we looked at how they failed over the next year. And you see the blue, it's pretty pronounced. The first 18 months of a drive's life, they're failing at, between 3 and 10% per quarter. Each of these lines is a quarter. And then things settle down for a year or so, and then we're back up to high failure rates. In 2021, we repeated the exercise, and we found that actually there wasn't such a pronounced front edge to the bathtub. There's variation here in the red, but there's still, wow, at the end, these drives are wearing out hard after 7.5, 8 years. And then when we did it this year, it kind of followed a similar pattern, but it's kind of longer. We see over time that drives are lasting longer. You can expect a drive view by today to probably last 8 to 10 years. And that certainly wasn't the case 12 years ago when you were seeing like these really high rates coming into 4 years.
It's significant to know here as well that we have changed our drive management practices over time. So when we say you can get all the way to 10 years without a failure, that means we've retired drives that have never failed, right? Because there's a question there of like, oh my God, if my drives are getting older, I have 100,000 Seagates that are over 8 years old. You just don't want to have a situation where all those fail at once. So when we see this end where there's a high failure rate over here, there's a whole population of drives just never failed. It's pretty cool.
Yeah.
Yeah.
Yeah, when we say we kind of run the drives to death, that's actually a lie.
It's a little bit of a lie.
Because we do say, okay, we're going to take these drives out of service. And I'll actually get onto that when we talk about our old friend, the Seagate 4 terabyte. So right now, in fact. So this is, if you do a sorted table of drive model by count, Seagate 4 terabyte is at the top, this DM000 model. We first installed 45 of them in May 2013, and by a couple of years later, they made up more than 50% of our fleet.
Yeah.
And many of these drives have exceeded, 8.5 years. And in fact, when we've retired them, it's usually been because we want to make more efficient use of that space in the data center. Because if you think we've got pods with 4 terabyte drives, and say at the time the current technology is say 16 terabytes, you can get 4 times as much storage in the same floor space and power consumption. So at times, we've actually taken drives out of service just to get more storage into the same space. And so what you can see here, this is the same kind of chart. Again, there's a little front lip to the bathtub here. Things settle down quickly. And these things go and go and go and go. And then it kind of goes wild at the end. Well, if we overlay the drive count, we can see why that is. Because we've got big population of drives that are contributing to the failure rate over here. And then this is, the population reduces. So these are the ages of the drives for these failure rates. So it's like, okay, you've got like natural attrition here. I think here at about 4 years, we replaced some. Again, another of these kind of gradual dips, and then it's okay. These are getting old now. We really have to take them out of service. So the effect is that as the drive count falls, this failure rate gets more chaotic, because just a drive failing one quarter rather than the next makes a huge difference, makes a huge spike here. So don't pay too much attention to the end here, but it is possible to kind of like, derive some kind of trend here, an upward trend to the far end of the bathtub. And the interesting thing here is, I'm going to extemporize now. This is not in the script. I've had statisticians talk to me about, okay, well, why can't you model this thing? Why can't you kind of look at all the data you have, and maybe at this point you can project what's going to happen in the future? And the problem is that each of these drive models, so not even manufacturer to manufacturer, model to model, have different characteristics, different lifetimes. So we always know there's a bathtub. We never know how long the bath is going to be. So we literally have some certain drive models, and they've like failed years earlier than we expected, because it was just not a good model. It was a lemon. So our current cohort, we did some analysis on the 20 terabyte plus drives. So these are the latest, greatest, and they haven't been around for long. So for this Toshiba, 11 months of data, not much of a trend there. Is it? We can maybe say, okay, the highest point was right at the beginning here. There's like some brand new drives that almost dead on arrival, and then it settles down. But numbers. This one's much more interesting to look at, because there's a clearly discernible trend here of high mortality, 1.2%, 1.5% in the first couple of months of introduction, and then things settle down. And this drive count, it has this shape because these are drives that we're rolling out. So we've got lots, we've been introducing them so many per month for the past couple of years. So we've got lots that have lasted at least 0 months, and then a few less that have lasted at least 1 month, blah, 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 blah. And then over here, these are the drives that we've just rolled out just before we took this chart. So pretty interesting to look at a single drive and see that pattern. And then the Seagate, 6 months again, who knows? It's higher, it's kind of oscillating around 2%. Could be less reliable, but is there enough data to make a determination? And so we can put them all together and see, okay, the Western Digital has a lovely pattern there, and really we want more data on these to see how they're going to shape up. And putting them together as a pool, that Western Digital dominates just because of the amount of data we have compared to the other ones. Now, if we go back, and by the way, we included these tables so that if you do go and download the PDF, you can stare at these at your leisure. If we go back and look at the previous generation of 14 to 16 terabyte drives, we kind of see a similar pattern, but different. There's, again, high infant mortality, but it settles down very quickly into this kind of 0.75% range. So we've got very predictable attrition in our drive population for this initial couple of years. So we snapshotted that just so that we're comparing apples to apples. But then, of course, these drives are much older, so we actually have way more data. So again, we can see very stable here, and then just creeping up, getting closer to 2. And then as the drive count falls, just these are not statistically significant, but it's cool to look at. Okay, so what are we calling out here? These are the current failure rates for these drives. So as a group, about 1%, which is pretty good. And these orange ones, over 4 years old. So Seagate, not so good. Toshiba, middling. These Western Digitals,
14s are great.
currently this crop seems to be pretty reliable. Okay, Steph, tell us about solid state storage.
Can do. All right, so in addition to, hey, what manufacturer is the best, one of the things we often get is, why don't you share statistics about solid state drives? I love answering this question because it gives us the opportunity to talk about, how the technologies are fundamentally different. So right now, hard drives, as we've said, still make up the vast majority of storage. And the reason for that is that you get a ton more bang for your buck as far as actual storage goes, right? So we're still at $17-ish per terabyte, and whereas SSDs are about $112.50 per terabyte. But there are instances where you might want better performance. So you can see the latency, the throughput on solid state drives is significantly different as well. But when you're talking about moving data drives, keep using these as storage drives, you don't always need that kind of speed. So when do you? Well, this led to, first, we did try to share SSD stats at one point. Right now, we largely use SSDs in our data centers as boot drives, right? So they tell other drives what to do. The problem with that is that some of these drives have a population of like 3, right? So if one of those fails, all of a sudden you're like at 100,000,000% failure rate. It's insane. And I think we did a really good job of contextualizing, the problems with reporting on these when we shared the report. So if you want to go check it out and sort of see if there's anything significant for you in the data, please do. But when it comes to comparing apples to apples with what the drive stats population does, it's not the same, right? So we have started using SSDs. Since that first report, we've started using SSDs in some capacity in our data centers for storage. What we've done, so Pat talked a little bit about the fault structure, how you have 15 pieces of a file, 5 parity shards, and that lets you rebuild a file if you have any one of those pieces, essentially. But when we don't return, if you were to upload a file to Backblaze, we're not going to tell you that we've got it, you're good, until all 20 of those parts are written. And when you are thinking about how files get routed and then stored within our data center, empty pods or empty storage servers actually get more of the traffic than other ones, right? So if you have a bunch of small files you're trying to upload, we're going to fill those biggest servers first, because what our system knows is like, hey, this guy's got a lot of available storage, like send him stuff. So that means that when you're trying to write to Backblaze, that can be a really long time you're waiting. So what we did is create essentially a caching layer where we will write your file, especially if it's a small file, to an SSD. We'll tell you we got it, and then you will have confidence because it meets all of those standards for parity. And then we will move it later. So as you can imagine, that is a very different use pattern than a boot drive. Oh my goodness, it is so different. So if we were to release statistics about our SSDs today, you would be looking at completely unintelligible numbers. We are doing a lot to figure out how we can track them, and that's when you get into those, you saw in the metadata, some things that we can track, like where things are in data center, pod ID, all that good stuff. So potentially room for it in the future, but at the moment we are like, we can't stand behind those numbers. And that brings us to the end of our presentation. We'd love some questions. Anybody? Yes.
Do you think you've had any impact on behaviors by manufacturers, and have they complained on various things you've done?
Do you want to repeat the question for the tape?
Yes. So great question. Have we impacted drive manufacturers, and has there been any repercussions for said situation? If you know anything about enterprise drive writing, these are very complicated, delicate relationships, right? Everybody needs them. There's only a limited amount. You're getting in line. The gentleman in our company who has this job, I respect so much. I've heard tell, Andy told me, that one of the earlier, when we first started releasing this information, one of the earlier conversations he had was like, he was at a booth at a trade show, and like somebody just casually came up and was talking to him. So I know that there have been conversations. You've got, I think, a better story though.
Yeah, so I can't remember if we've in the past named the manufacturer.
I'm steering away from that one.
One of the manufacturers wrote us a cease and desist letter. This is my understanding, my recollection. And I certainly know that Andy Klein was deposed by this manufacturer's lawyers and had to explain that we are merely reporting our experience. There is no malice. There is no untruth. These are our observations of running these drives in a production setting. So, if you want to make the numbers better, make better drives. So,
No.
no, not on the tape. We can talk about it later. But even at our size and scale, we are something of a minnow compared to the hyperscalers, and so I don't know. It's difficult to say. We buy from. I mean, there's 3 manufacturers left, right? Toshiba, Seagate, and Western Digital. And we buy from all 3, and we validate the drives, and we have a good idea of the performance. We wouldn't necessarily buy the same drives as you would, because if you're running a NAS, it's a big load of hassle when a drive fails, right? You've got to take it out, you've got to restripe it, you're at kind of like reduced reliability for a few days while you're doing that. We, in our data centers, maybe have like half a dozen drives fail a day. And so if we want to say, okay, we can save a bit of money by buying this drive, which we know is going to be less reliable, but we save enough that going from changing 6 drives a day to 10 drives a day, we don't care. Mm-hmm. And we're getting a good deal on that storage. So, it's interesting when you look at the interplay between manufacturers and consumers and providers. Like, there are different patterns there, and I don't know if we influence their behavior. Maybe they don't tell us.
Yeah.
They won't admit it.
I mean, quite interestingly, like there's already a little bit of a feedback loop that we have that consumers don't, which is that we have enterprise drive warranties, right? So up until 5 years, they're going to kick us a new drive if they see model failing, especially significantly. So when we do get a lemon of a model, yes, sorry, terrible at mic control today, y'all. But when we do get a lemon of a model, it's immediately apparent. So I know that there are certainly ways that we test and validate drives that we have conversations directly with manufacturers.
Yeah,
that's as much as I can say.
Yeah. Which there's certainly been firmware issues where we've been in deep discussions with the manufacturer because they just have not been apparent until the drives were being run, not partly at the scale and partly the way that we run them, like spinning them 24/7, and we bring a new vault into service and that gets all the new traffic. So those heads are really working hard. And incidentally, I thought of this while we were talking earlier on about, as drives age, just the natural access patterns, as data ages, it's accessed less often. So just the head movement on those drives tends to settle down over time. So, that's, the traffic in our data centers is going to the newer drives. And again, these are patterns that you won't see with your 5 drive, even 10 drive NAS. Because we've got tens of thousands of drives, we're steering the traffic around, and then we have all of these, say, 12 terabyte drives that are still spinning, data's still available at 100 milliseconds latency, but it's just not being accessed that often, so the drives have kind of got an easy life.
I'm going to add,
to
add one more thing there. So I was talking about validating drives, and what's interesting is that we talked about storage density and all these good things, right? You can be limited by different types of things that you can't actually see in testing, right? So the Pat reference firmware, the order in which a drive decides to execute operations it has, read, write, delete, that is not apparent until you hit production. So you can be testing this drive and be like, oh, I don't love its performance, I don't love this about it, and then it gets in production and it's a rock star because it chooses to, its firmware tells it to do that differently than a comparable drive, same size, same manufacturer. It's just what it is. More questions?
Command queue management.
Command queue management, very exciting. I love my job. Go ahead.
So just a quick one, I know you
Yep.
said you track different stats.
Yes.
Obviously, like temperature, but we also check whether vertical or horizontal orientation impacts lifetime. And also, like, obviously when it ages out, we also track to see if somebody suddenly does a restore, it actually takes out your tools.
Takes.
That basically impacts the tools and causes failures.
Okay, so the question up here is, have we ever done an analysis to see if the drive's vertical or horizontal position within a server impacts its lifetime? And then separately, if we have an older drive, if running a restore from that drive will impact its lifetime or restore. I don't know that we have done the second question that you asked. I don't even know, I mean, can you think of what fields we'd use to even run an analysis like that?
So in reality, the orientation is set by the need to have them in whatever it is, 5U boxes slotted into a rack. So the short answer is no, because we haven't had we just don't run them horizontal. And then the second one, so you're asking about running a restore. You see, in our data centers, everything is so spread out that so when you restore a data set, you're restoring it from 15 drives out of we call it a tome of 20 that it's been sharded across. So we're not, and for a particular customer, as they're kind of restoring different files, it can be like ping, 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 ping around the data center.
Yep.
So everything's kind of smeared out for us. So we don't see those effects. To some extent, yes, because we'll bring a new vault online and it's empty, so it'll get a lot of traffic. So there is an effect that a particular vault will have a particular vintage of data, but again, it's kind of smeared out a little bit because files get deleted, the space gets reused, and it's kind of it's almost like a sedimenting over time.
Yep.
That you get to the point where you have vaults that kind of they've just got like people, customers' archives and all that data that has to be kept around for 7 years and then deleted on the very next day when it ages out of having to keep it for compliance and all of that stuff. So
One thing to add there, we actually can run analyses by server location. We haven't, but I know in the past we've been able to see like basically hotspots in our data centers and then alert our DC techs. That's something we can absolutely do. And we fixed them, right? And we do. There is some. But there was the really hot summer 2 summers ago, right? And we did have drives that exceeded their allowed temperature, right? So we have a pool of drives we're actually watching. We got a real world experiment happening. It's awesome, right? But what we found is that when they came back online, they were actually performing more or less the same. So we're kind of like, let them ride, see what information we can get, particularly because it's not a huge set of drives, right? So we're covered by redundancy and all that good stuff. Yeah, over here.
So you guys drilled a little bit into my question that I had.
Sure.
You had mentioned earlier that you have so many drives, so many different locations that you might have an ability to tell, hey, do drives fail more at night, during the day, in summer?
Oh, data access patterns.
The earthquakes on the West Coast every once in a while, and that affects our drives. So what kind of weird stats? I'm just curious.
we make this data available to you. Go nuts. You know, the potential is there. We've done some of those analyses, mostly around things like temperature, operating temperature, and so on. I don't think we've ever looked at West Coast versus East Coast specifically, but because we haven't been, those are fields that we added relatively recently. So that, physical
like
location.
4 quarters or
That's
so ago.
Yeah, just in the past year or two.
Yeah.
So probably need a little bit more data to get to the point where we can start saying, okay, let's slice it this way and see what happens. You know, one of, like I mentioned earlier, one of the interesting ones is the drive's location within the server. You know, is that significant? You know, is there a correlation with failure? But you need a lot of data to get statistically significant results.
But we do have a series called Network Stats, run by a gentleman called Brent Nowak. He's brilliant. He's done webinars with Pat, actually, and he identified a bunch of our data access patterns. So traditionally, if you know anything about Backblaze, we were largely a backup provider. Now we do way more cloud object storage, application storage, all that good stuff. So things like people run backups at midnight are absolutely visible in that data. So please, again, make the data available, go nuts.
Yeah. And then in the middle?
Attempting to use drive stats to identify like bad batches of drives that you want to preemptively remove from the fleet.
Yeah, no, there have definitely been instances where a particular drive model has revealed itself to be unreliable, that we've picked that up through drive stats, and that's prompted, you know, a deep dive to say, okay, do we need to rotate these out? So yeah, that happens. Yeah, in the back.
Relative to the amount of drives that are in the system, so like, how many drives do you need to have in operation for you to believe that the statistics presented have any real impact on decision?
Right. So the question's like, how do we decide that the results are statistically significant? Essentially, yeah. So if I was to backspace like crazy through the presentation, or if you look at the tables on the blog, what you'll see is that for those quarterly and lifetime stats, we set a cutoff to say, okay, there has to be over, say, 500 drives in operation, and we have to have seen at least 100,000 drive days of activity. So there are more statistics that we kind of cut from those tables because, you know, there aren't enough drives for those figures to be, you know, reliable, to be statistically significant, to draw conclusions. So yes. Okay. Yeah, again in the middle.
Do you have a feeling for how far off we are from the break-even for data density and power costs for SSDs versus steady disks?
Ooh, the $64,000 question. When are we going to break even for SSDs and hard drives?
Oh.
Well, not soon, because what is it? 6 times more expensive per terabyte.
Have you
But
factored in like power and space in the data center?
yeah. Oh, yeah, for sure. I mean, you better believe we have people staring at those numbers constantly. But right now, it makes sense to us to deploy SSDs kind of strategically, like with Shard Stash, where they can make a big difference in those small files where just the F-sync operation, you know, like pushing the data down to the media with small files is a huge part of the time, like the turnaround time. Mm-hmm. And so what we're able to do there is say, okay, well, let's use SSDs for those because it's going to make a big difference for applications that, for whatever reason, use small files. Rolling, I think what you'll see, and this is me just speaking, you know, off the cuff, is you'll see us using SSDs more, but in a kind of like a phased strategic way. Maybe one day it'll be the case that, you know, we turn off the last spinning disk and our data centers are much quieter and cooler and everything else. But, you know, I gotta say, looking at the, you know, the trends so far, that day is still pretty far off.